Good afternoon. Let's continue with where we ended. We are looking at the Starlin forces across the glomerular capillaries. Starlin forces. Now, as in the systemic capillaries, capillaries elsewhere other than the kidneys, the pressure that drives fluid movement across the glomerular capillaries are the Starlin pressures or Starlin forces. We know that capillaries, this is where there is site of exchange of materials, okay, from cells into blood. That exchange of materials occur at capillary beds. So there are two forces, there are basically four Starlin pressures that act at the capillary bed. Two of these are called hydrostatic pressures. One is in the capillary blood and one is in the interstitial fluid. And the other two are oncotic pressures. One is in the capillary blood and one is in the interstitial fluid. So what does the Starlin hypothesis state? The Starlin hypothesis states that the net filtration through the capillary membrane is proportional to the hydrostatic pressure difference across the membrane minus oncotic pressure. Starlin hypothesis states that the net filtration through capillary membrane is proportional to hydrostatic pressure difference across the membrane minus oncotic pressure. This is a filtration barrier. We want the fluid to penetrate this filtration barrier. Okay. So there is a major force, we call it the hydrostatic pressure. Okay. We call it the hydrostatic pressure in the capillaries. These are the capillaries. This is a Bowman space. Okay. So this pressure doesn't just pass through anyhow, because there's a membrane here. Okay. So for example, if the pressure, let's say it's 40. When you measure it before the membrane, when you measure it after the membrane, you find that maybe it has reduced to 20. Why? It's because of the Starlin forces. These are forces that drive fluid movements across the glomerular capillaries. There are four of them, which you are going to see. So these are the four Starlin forces. There's a glomerular capillary pressure. There's a colloidal osmotic pressure in the glomeruli. There's a hydrostatic pressure in the Bowman's capsule. And there's a colloidal osmotic pressure in the filtrate in the tubule. Okay. Do not get confused with these terminologies. Glomerular capillary, it means the hydrostatic pressure. The actual pressure, which is determined by what? By the pumping action of the blood or of the heart. It is called the hydrostatic pressure in the glomerular capillaries. Okay. So, what can we say about the glomerular capillary pressure? We can say that this is a force which favors filtration. When compared with the systemic capillaries, the glomerular capillary pressure is relatively high. It's about 45 millimeters of mercury. Okay, this is one of the highest hydrostatic pressure you can find in the capillary bed. It is located in the glomerular capillaries. In the systemic capillaries, hydrostatic pressure falls along the length of the capillary. In the glomerular capillaries, it remains constant along the entire length. And then we have the colloidal osmotic pressure in the glomeruli, meaning in the capillaries. Okay. This is also called oncotic pressure in the glomerular capillaries. This is another force opposing filtration, and it is determined by proteins, concentration of the glomerular capillary blood. Oncotic pressure does not remain constant along the capillary length. Rather, it progressively increases as fluid is filtered out of the capillary. and the oncotic pressure eventually increases to the point where net ultrafiltration pressure becomes 0. Okay, and then filtration will stop. And then we have the hydrostatic pressure in the Bowman's capsule. It's similar to this, but this one is the hydrostatic pressure in the Bowman's capsule. Okay, what can we say about this pressure? This is the force opposing filtration, and then the origin of this pressure is the fluid present in the lumen of the nephron, which is about 10 millimeters of mercury. And then the last one is the colloidal osmotic pressure in the filtrate, also called oncotic pressure. Oncotic pressure in the Bowman space. This one is usually 0, okay, because we don't expect any protein to be present in the filtrate unless in pathological conditions. And then there is this Kf. Kf is just a constant called the filtration coefficient. It measures permeability or conductance of glomerular capillary. We won't talk about Kf a lot. We just need to know that it measures conductance and permeability of the capillary wall. Okay. So this is what I'm talking about. The pressure acting at the renal corpuscle, these are the forces. There's a major one, which is called the hydrostatic pressure in the glomerular capillaries. This one is opposed by the oncotic pressure in the glomerular capillaries. But the hydrostatic pressure is also opposed by the pressure in the Bowman's space. Okay? Hydrostatic pressure in the Bowman space. Together, when you do your mathematics, they should give you a net filtration pressure of 16 millimeters of mercury. They should give you a pressure of 16 millimeters of mercury. Okay. So these values, when you incorporate them in the Starlin equation, you're going to find positive 16 millimeters of mercury. Of course, you can just ignore these constants. Now, what changes in the Starlin pressures? Changes in Starlin pressures. The GFR depends on the net ultrafiltration pressure. Okay, that's why GFR is equivalent to the ultrafiltration pressure. Okay, and the GFR also depends on the sum of the Starlin pressures across the glomerular capillary wall. It should be clear, therefore, that changes in GFR can be brought about by changes in any of these Starlin forces. Okay, changes in the GFR can be caused by changes in any of these Starlin forces. For example, if there is change in hydrostatic pressure in the glomerular capillaries. Okay, first of all, what can cause this to change? It is produced by change in the resistance of afferent and efferent arterioles. When they constrict or dilate, they will change the hydrostatic pressure in the glomerular capillaries. Okay. For example, when there is constriction of afferent arterioles, or in other words, when there is increase in arteriolar resistance, what do we expect? The renal plasma flow will decrease, and GFR will also decrease, because less blood flows to the glomerular capillary. And therefore, PGC, which is hydrostatic pressure in the glomerular capillaries, will decrease, which will reduce the net ultrafiltration pressure. Okay. This can be observed when there is during the sympathetic nervous system activity, or where there is high levels of angiotensin 2. Okay. But it's opposite when there is constriction of the efferent arterioles. Okay, when the efferent arterioles, this side, when they constrict, that is when the diameter becomes narrow, the effect of arterial constriction on the renal plasma flow is the same as with constriction of the afferent arteriole. Yet, the effect on glomerular filtration rate is opposite. Okay? Glomerular filtration rate increases because blood is restricted from leaving the glomerular capillaries, causing the PGC and net outer filtration pressure to increase. An example is where there is low levels of angiotensin 2. Okay, so we can talk a lot about these equations, but I've summarized them in this diagram. Okay, effect. Constriction of afferent arterioles. What's the effect on renal plasma flow? It reduces. What's the effect on glomerular filtration rate? It reduces. What's the filtration fraction? No change. Okay. So the way they decrease these, it's in proportion. Okay, they decrease by a certain factor. That's why there's no change. The rate of decrease is similar. Okay. And then constriction of efferent arterioles. When they constrict, the renal plasma flow will decrease, but the glomerular filtration rate will increase. And the filtration fraction will increase. Okay, so you can also look at these other parameters. Okay, these are the same things we're talking about, the constriction of afferent arterioles. This is what really happens. And then there's also constriction of efferent arterioles. And then net filtration pressure is just when you subtract glomerular capillary pressure minus the sum of colloidal osmotic pressure plus the hydrostatic pressure in the Bowman's capsule. Okay, which can give you about 20 millimeters of mercury. Okay, so this is where we end. So we can say that the Starlin forces, these are the forces that act at the capillary beds, and changes in Starlin forces can even lead to conditions such as edema. Okay, for example, when there is increased hydrostatic pressure can lead to edema. Also, when there is decrease in the oncotic pressure can also lead to edema. So in a normal healthy person, these forces, when you add them together, they should give you a net filtration pressure of 20 millimeters of mercury. Okay, so we'll end here. The next we'll look at reabsorption and secretion.